Now that we understand a bit about how people vary physically, it's important to learn the basics about how they perceive, interpret, make decisions, and act. The way that humans take in information, interpret it, make decisions, and act is complex, and there are numerous theories about how this process is completed, the feedback loops that occur, and the parallel processing that goes on. For the purposes of this course, we're going to simplify things by discussing a model that's used for talking about automation, the model of automation support. By using this model, we can discuss some of the considerations that you may apply to your design without delving into too much detail. Just know that although this model covers basic steps, it's not fully reflective of the human information processing. What you need to know as a designer is, can the user group sense or detect the information we want them to, process the information, make a decision based on it, and then complete the necessary action. We can look at a simple example like hunger. In step 1, you're hungry. Your stomach releases acids and clenches, which activates sensors in your stomach lining. The sensors send signals to your brain. Your brain receives and decodes the signals as signs of hunger. That's step 2. Step 3, you have to make a decision. Do you get something to eat or do you continue to work? And step 4 is your action. Errors can occur at each one of these 4 stages during any type of on-aircraft activity, but we're going to focus on the man-machine interface as it relates to a pilot. The first step is sensing. Every second, you're sensing an incredible amount of information, sensing all that I say, all that I'm showing you, other things happening around you, and much more. You acquire information through all 5 of your senses, plus proprioception and your vestibular senses. You can sense a lot of information, but you can't process it all. Much extraneous information is filtered out by your brain. How your tongue feels in your mouth, for example, how your wristwatch feels on your arm, or your belt around your waist. These are repeated stimuli, which usually are ignored. Another example is a continuously blinking light. These stimulus only get our attention when something attracts it, so the light changes color, for example. There can be errors caused by damaged sense organs or damaged transmission systems. The process can't start if the sense organ doesn't function. But as designers, you can assume that air crew and ground crew can see and hear normally, as these are requirements of their jobs. You might be thinking, how does this relate to design? Basically, when you're designing a cockpit, you need to make sure that the person is able to sense the right information at the right time. You give them the necessary information without providing too much so that they ignore the important stuff, and without providing the information too often. One of the best examples of this is the gear up indication. You want to make sure that the alarm sounds only when the person is intending to land and when they've reached the point where they should have put the gear down. If the alarm sounds too often, too soon, or does not capture their attention, then they could simply ignore it. After sensing comes information processing, where information is manipulated or processed and then integrated into working memory. It is in this stage that the brain infers things, basically where it makes sense out of the information. This is the stage where biases, expectation, and visual illusions play a role. An example of how you could apply this to the aircraft design is to ensure you're not giving the person mixed messages, which could cause problems when they're trying to interpret the information. A GPS display, for example, that shows the person moving in one direction when they in fact can see or feel that they're moving in another. Such mixed messaging could be difficult for the person's brain to interpret. The third stage is decision making. Once you've drawn conclusions, rightly or wrongly, about the meaning of what you've perceived, you move on to deciding what to do. Many factors are considered, and there's a whole bunch of different decision-making strategies employed by people under different circumstances that we won't go into. Training and experience are a big influence on how a person treats a situation and how information is analyzed to reach a decision. An important feature of decision-making or active thought is that a person can handle only one thing at a time. People have a huge capacity for sensing information, but decision-making can handle just one channel, one piece of information at a time. Other information is shunted away into short-term memory, which is notoriously unreliable, to wait to be retrieved when the decision-making channel becomes free. It's easy to overload the decision-making channel. This is essentially a speed versus accuracy trade-off. The impact of this on aircraft design is that we want to try to design things in such a way that the pilot or maintenance technicians are not overloaded. After deciding what to do, now the person must carry out the action they decided upon, or not act if that was the decision. Muscles will be directed to manipulate controls or tools or speak instructions. But this is yet another stage where error can be a problem. If you intend an incorrect action and carry it out, this is not considered a problem with the action, but rather something in the previous steps that led to the wrong decision. If, however, you intend something quite different from the outcome, this is considered an action error. If the control or tool is badly designed from a human factors standpoint, the intention and decision could be correct, but the action actually wrong. There is again a family of influences that causes incorrect actions. This is the cockpit of an Airbus 380. Look at the image while I talk about some of the things we can do to help make actions easier in an aircraft. First, we follow the importance principle, which is to put items that are the most important or critical in the primary reach area. Next, we follow the frequency of use principle, locating things that are used frequently in an easy-to-reach area. Note that importance always supersedes frequency, so critical controls must be in the primary reach area. We also follow the functional grouping principle, grouping related components together according to their function. After this, we follow the sequence of use principle, so that components are arranged in the order that they're used. Now we get into the controls themselves. To ensure pilots select the correct controls, we use tactile and visual dissimilarity to help them differentiate between controls. The symbols that we use in an aircraft relate directly to the real world. The way controls function are also related to the real world. So up for wheels actually moves the control, you move the control up. Finally, the force required to move the controls should not be excessive, but should offer enough resistance to ensure the person senses that they're moving it. And finally, going back to anthropometrics, we need to make sure that all the people in the population can physically complete the task, reach the control, or see the indicator light.